Okay, I guess we can start. So today, basically, what we're going to do is like discuss different type of interpolation, which are these like splines, or more specifically, we're going to talk about the cubic splines because I think that they turn out to be particularly useful. So, if you remember, kind of what was happening yesterday when we talked about Lagrange interpolation, one of the things I said, if you remember this Roentgen example, is that depending actually on how the points are distributed, the Lagrange polynomial can kind of like fluctuate very wildly. Um, so it's not like it's not the end like completely bad because you could like sometimes choose like a different point distribution or spacing of the points. But if you think about it more like from like actual data points where you don't have control on what the values for X is going to be, then that could become more problematic. So it's kind of like useful to know about certain alternatives out there to like the Lagrange interpolation method. And this is one of the alternatives is like the cubic splice. So I'll kind of like explain a little bit first about what the idea is, and then we'll work out some special cases so that you see how it looks like. Let me see if I can open my GeoGebra first. Okay, so in this example, like the way I have it set up, like a very simple interpolation problem where you only have 3 points, right? Um, So, kind of like the philosophy from yesterday, if you had tried to do Lagrange interpolation, would have been okay, you have 3 points. You would find try to approximate or try to interpolate with a polynomial of degree 2, which is a parabola, right? Because it's always 1 degree less than the number of points you were given. So in this case, you could use Lagrange interpolation to find the approximating polynomial, and that's totally fine. An alternative perspective is to say, okay, I'm not going to try to find a single polynomial that passes through all the points. Rather, I'll kind of uh, try to find like a family of polynomials that interpolate kind of like 2 points at a time. So instead of trying to find like a single curve, it's kind of like more like a family of curves. Which doing the interpolation. So just to show you like an example, like one way to like interpolate in this case could be like, well, I'll just join these 2 points with a line, which would be here, right? And I'll just join these two other points with a line, which would be this one, right? And so that is a kind of like as a function, it is a continuous function, right? In fact, it's piecewise linear because like on each interval, right? Like there's like an interval from -1 to 0 here and an interval from 0 to 1 here. On each sub-interval, the function is like a linear function, right? So this is something that you could call like a piecewise linear interpolation, right? Because you're interpolating with linear functions. It's just that it's not represented as a single like line because definitely would not work. Now, if you try to do this, right, kind of like the first thing that comes to mind if you look at this interpolation is that kind of like where the two lines meet, right? The function is definitely continuous, right? If you think about joining these two graphs, but where the two lines meet, the first derivative is discontinuous, right? There's kind of like a break in the first derivative, or like another way of saying this is like there is like kind of like a corner here. Like the function, if you thought about this as being like a single function, the function is not going to be differentiable at the origin in this case, right? Um, which makes sense because like each line has like the derivative of a line is like the slope, right? And these two slopes are different, so there's no way to kind of like make them coincide at the point where like the change in the definition of the function would happen, right? So interpolating with lines is not a great idea because then at the points where you're trying to kind of like where the line would change, then most likely what will happen is just like the first derivative would change values discontinuously, right? Is that kind of making sense so far, so good? So like like usually using a polynomial interpolation with line, kind of like a piecewise linear function has like an issue because the first derivative would no longer be continuous, at least like at the breaking. So okay, based on that, you could kind of like s try a slightly different thing, which is to say, okay, instead of like using lines to kind of like connect 2 points at a time, I could use parabolas. So for example, like these 2 points. Uh, These 2 points are connected by the parabola y equals x squared, which I don't know if I think you can see like on GeoGebra, like the formula for the function, right? So it's like the one that's being called here f of x. So like, for example, like the parabola y equals x squared passes through those 2 points, and the parabola y equals minus 2x squared passes through those 2 points, right? So again, now this is kind of like a piecewise quadratic function, right? Because on each of the sub-intervals, right? Like the function is a quadratic, like a parabola. Um, and for example, at least if you choose the parabolas this way, it does have the advantage in this case that if you look at the first derivative, right? Like the first derivative for the first one is what, 2x, and for the second one is minus 4x. So they do agree at x equals 0, right? Like they both give you 0. So now the first derivative actually has no issues, right? Like the first derivative does, it doesn't jump in values. But now the problem with this parabola type interpolation is that the fourth, no, sorry, I think I said fourth. Like the second derivative is problematic, right? Because what is the first derivative? Sorry, what is the second derivative of the first parabola? The second derivative of the first parabola would be what, 2, just like the number 2, right? It's concave up also, and the second derivative of the second parabola would be -4, right? One is concave up and the other is concave down. So the second derivatives now, like, you kind of like change the problem. So now the first derivatives were fine, but the second derivatives were the ones with an issue, right? And so that means that at this point where like the break like the definition changes, the second derivative could jump, right? Could change values in a discontinuous way. And that's kind of like an issue because, you know, when you have a function, like the first and second derivatives are really important, like pieces of data of a function because, like, like the first derivative is related to critical points, max mean, the second derivative to concavity, you know. So like you would like to have like an approximation or like an interpolation where like the first and second derivatives kind of like behave well throughout the entire process. Okay, so kind of like is that making sense? So hopefully you see where I'm headed. So kind of like the idea would be, okay, maybe you can try a degree higher, which is what we'll work with today. So instead of like, for example, trying to find like a parabola and a parabola passing through each of these 2 points at a time, you could try to find a cubic polynomial and a different cubic polynomial passing through the points and try to kind of like make it choose them so that like the second derivatives are like never jump. Okay. And that can be done. And that's kind of what we're going to work out today. And that's called like a cubic spline. So a cubic spline would just be kind of like finding a family of cubics that kind of like interpolate through the points, and the first and second derivatives like are always continuous functions. Okay. So there's no jumps in the first and second derivatives. And that actually they end up being very useful in practice. Um, so it is one of like the more popular um, methods, like for like interpolating. Like actually, let me see if before I write down some things on the board. Sorry, not on the board, on the tablet. Let me see if I can show you another animation that I had kind of like here. Um, so yeah, I'll also post this one on the Canvas side, so in case someone wants to play with them. But let's see. So yeah, like here's like kind of like a spline this is or a cubic spline. This is how this is going to be called, where instead of like um 3 points. Like for example, you're given 4 points, A, B, C, D, and kind of like the idea is that between any of these 2 points, okay, kind of like what you want to do is find between any of these 2 points, like of course consecutively. So between A and B, you find a cubic that passes through them. Between B and C, you find a cubic that passes through them, and between C and D, you find a cubic that passes through them. So these like the cubics are like red, blue, and green if you see them here. And kind of like the idea is to ask for the cubics to kind of like when you choose the cubics, what you want is to choose them in such a way that the first and second derivatives match at the point B where like the function changes, and then the first and second derivatives match at the point C where the function changes. Okay, this is funny. Actually, GeoGebra was started, I think, in Germany, so that's why there's like a lot of like of these animations in German. So but it's kind of like he's writing like or like the person is writing here like that the first derivatives that the first derivatives should agree and that the second derivatives should agree as well. I'll talk about more in a moment about the first and last equations, um, because that's like not you'll see why that's useful. But at least like on what I said, um, what you would like is kind of like the agreements of the first and second derivatives at the points where like the function would change its definition. And kind of like what I like about this animation is that you can kind of play around with the points, like moving it along, and you can kind of like see how the spline, like the cubic spline, is supposed to change. So it's just kind of like fun. Uh, okay. Is that making sense? Kind of like the setup. I'll write down now some stuff on the iPad, but I just wanted to kind of like motivate the idea behind it. Okay, so let me see if I can write. Let me start writing down some stuff. Oh, well, maybe before I do that, like I think most of you already logged in by now. So I posted, so the splines will be the last topic for the exam. I think I sent an announcement about that yesterday. I posted the study guide, so you can find it already on modules. So, wait, where is it? Oh no, okay. I think I uploaded let me see if I can upload it. It, uh, Oh yeah, I had added it as a file, but not on the module. Sorry about that. So now you can find it here on the Canvas side as a mod on the modules, and basically, like it says like the sections of the book that will be on the exam. But if not, like I kind of gave something a bit more specific of what my expectations are of what you should know how to do for each of the methods, like we have seen. Um, Kind of like my philosophy is more like, if you have, I will add some more practice problems on the PDF of problems, but kind of like if you have gone through all of them, then the exam is basically like the practice problems with like different numbers, like more or less. Like there's not like, I will provide. So I think I'll do one. I mean, I'll do one question for each topic. So one, two, three, four. Well, maybe like okay, maybe six, I would say. But I'll do it 100 minutes long, since like we won't do anything else on like there won't be any class that day. So and since the class officially meets for like 2 hours, I guess there's no issue in like giving you extra time. So it would yeah, I'll do six problems, and you'll have like 100 minutes. So what, like an hour and 40 minutes to work on it, and then so that you have like some cushion time to do the upload and all that stuff. Um, and then I will give some formulas, but those are the ones that I put here in bold. So for example, yeah, you don't have to memorize the formula for Newton-Raphson. That's fine. And I also will give the formula for the Lagrange polynomial. At least like this LNI thing, like you should know what it means. But I think those are like the two most complicated formulas, like to memorize. Like like in the bisection method, there's really not much to like. You just have to understand how to find like some iterations. Like um, I mean, if I ask to find like elements of the sequence, like obviously it has to be like just like two or three because otherwise it takes too much time. But yeah, and the fixed point is also like a very simple like iteration scheme. So um but yeah, so if you go through the practice exam, sorry, so through the practice problems, then kind of like the exam problems will be more or less the same, but with different numbers. I'll add some more, but it's, like just like take a look at the practice problems basically. Uh-huh. If that's okay. But yeah, like today is kind of like the last topic I'll include on it on the exam. Is that okay? Is there any questions? Okay, let's see. Okay, so what I was saying is that about the splines, so the cubic splines. Okay, so again, I won't do kind of like the most general case because I want to give you an idea of how the method is supposed to work. So I'll write, just to do something a bit more concrete. I'll like, you know, I'll just write it down as if you had 5 points. You'll see that like once you have that, like it's kind of like easy to understand how it should be in the general case. Okay, but let's say you have 5 points, which I'll call x0, y0, x1, y1, x2, y2, x3, y3, and the last one, let's put it kind of like x4, y4. Okay. So kind of like the idea of the cubic splines is that here they're like if you look at the x values, if you look at the x values, there are basically four intervals in this. Like is yes, that's correct. There are four intervals here. So this is the first interval. This is the second interval. This is the third interval. This is the fourth interval. Okay. And so kind of like the idea of the splines is that um, you are trying to find on each interval. Let me write it down. So here's like the goal. You're going to try to find so in each interval you try to find a polynomial of degree 3, so a cubic. Okay, you will try to find. Okay, so I'll call the cubic polynomials again. Um, I'll call them S for splines. So I'll call them. Let's say maybe this is how the first one would look. I'll call this one S1 of X. Here's how the second one may look. So let's say is let's try to do it more like this. S2 of X. Then here's how the third one would look like. Oops, like that actually didn't pass through the point. Like the point is a little bit. Here's S2 of X. Then there's a third one that maybe it does something like this. It's 3 of x. And then let's say the other one is like this. That's 4 of x. Okay. So on each there are four intervals, so there are four cubics that in this case you would have to find. Okay. Um, with the so each of them will be a cubic polynomial, and they will have the following three properties. Okay. So the idea is that each of the polynomials passes through the like like the corresponding points, like so the polynomial with the following properties. So kind of like the first one is that the polynomials interpolate. So the polynomials are supposed to interpolate, so they must pass through the given points. Okay, so that's the first property, that they just pass through all these points that you wanted. Okay. The second property is that the first derivative, the first derivative is continuous. So like the values of the first derivative agree where at the change of the change of where the different intervals meet. Okay. So the first derivatives of each um of each of the splines, like that's how they will call I will call them. I mean, I'm writing this verbally. I'll soon write it as a system of equations, but it's kind of like useful to have like a verbal description first. So the first derivatives of each of the splines agree where the different intervals meet. Okay. And last one, that the second derivatives of each of the splines agree with the where the different intervals meet. It's kind of like the same, but for the second derivatives. Okay. Is that making sense? Like, are like the conditions themselves? Okay, so what I'll do next, again, to just make it a little bit more concrete, I'll show you kind of like how this looks like for the case of 3 points, because you'll see that you end up solving like a lot of, I mean, depending on how you set it up, you could end up solving a bunch of equations. So I just want you to see how, kind of like the general structure is, because kind of like once you understand how to do it for 3 points, you really understand how to do it for any number of points. It's just like, it's like a lot more like that. It just kind of gets unpractical to do it by hand. So like you would just put it like on MATLAB or something like that. So I wouldn't ask anything that involves more than 3 points, because it's just, you'll see, I want you to see like explicitly the system of equations, and you see, it just gets like really big. But it's kind of useful to kind of like see how like, everything plays out, and um, just to kind of like have like a more like a concrete grasp of everything. So let me uh, write the conditions. I'll write the systems of equations that you will need to solve for the case of 3 points, which again will be the focus of like the problems that you have to work on. Okay. The book, if you are reading the book, like it kind of like gives you the formula for the general case. Like, it's not like, and you can even derive it if you are interested. It's not that, it's really just like keeping track of indices. Okay. So let me do the case of like, in all detail of 3 points. So let me draw the 3 points here. So in this case, there are only two intervals, right? Because here's x0, x1, and x2. So there are only two intervals to worry about, which is great. So maybe this would be the first spline. Let's call this like the first spline, the first cubic polynomial. And then the other one would be here like the second cubic polynomial. Maybe something like this. This would be the second spline. Okay. So kind of because each of these has to be a cubic polynomial, right? Again, so here S1 of x, S2 of x is a cubic polynomial. So because each of them is a cubic polynomial, you can write down the general formula for a cubic polynomial. So what is the general formula for a cubic polynomial? It would be C0 plus C1x plus C2x squared plus C3x cubed, right? And then S2 of x would be this. Let's use another letter for the coefficient. So like let's use these. So it would be D0 plus D1x plus D2x squared plus D3x cubed. So basically here the goal would be to determine, you want to determine all the coefficients, right? So you want to determine C0, C1, C2, C3, D0, D1, D2, D3, right? So the goal is to find. Is that making sense? So far, so good? Well, it's cubic because you would like the if you use something of lower degree, you cannot guarantee you won't be able to guarantee for the first and second derivatives to match. Um, so if you try something linear or quadratic, um, then like it is not like that is not that's not enough parameters has that's how I would say it to kind of like guarantee for the derivatives to match. So kind of like the lowest degree polynomial you can attempt is a cubic one. I mean, you could also do it a quartic or quintics, but it's kind of like in practice, cubic kind of like ends up being convenient because it has fewer parameters, but it also has like this nice property that the first and the second derivatives can be forced to coincide where the intervals change, which you wouldn't be able to with a line or with a parabola. But there's no like philosophical reason for why it's cubic. I mean, it's just kind of like a practical, it's like a practicality thing. Like, like again, you could like try to interpolate with quartics or other things. It's just like it's like a big, like, then you'll see, you would have to start adding extra and extra conditions. So kind of cubic just ends up being the lowest degree polynomial that kind of like makes this work out nicely. Yeah. But if you wanted like the third derivatives to match, like if for whatever reason in your application the third derivatives are important and you want the third derivatives not to have jumps, then you would actually use quartic polynomials, for example. It's just that in most applications, like the first and second derivatives are kind of like the really important, you know, derivatives of a function. So like those are the ones that you really want to make sure they don't jump, they don't change values like abruptly. Okay, let's see. So you have to find eight constants, like eight parameters, right? And so in principle, that does require like eight equations, right? So we just have like what I want to show you is explicitly whether what I like the conditions that I mentioned earlier um, give you enough equations to determine them uniquely. Because again, like an algorithm, I guess I haven't said this like too out loud, but kind of like the idea of an algorithm for it to kind of like be useful is that you don't want any freedom in determining the constants because like like the idea is like the result should be unambiguous, so you want to know that you have actually enough equations to pin down all the values because otherwise there would be like this like wiggle room in finding them and like if you want to put that into a computer like then how do you deal with that. um so the first like there are three equations that you get for free. Well, I'm actually four. I mean, three there are 3 points. Okay, and so the interpolation condition is that S1 should pass through this point and this point, and that S2 should pass through this point and this point. And that actually gives you, so you get two equations, one for each spline. So kind of, let's call these interpolation conditions. So like, or the interpolation equations, which is that S1 should pass through X0, Y0, and X1, Y1. So S1 of X should pass. Okay, and that gives you two equations, which would be what? It would give you that if you put x0, you get c0 plus c1 x0 plus c2 x0 squared plus c3 x0 cubed should be y0. And then you get the same with x1. Is that okay? Is that making sense? And then you get two more equations by asking S2, the second cubic, to pass through x1, y1, and x2, y2. So S2 of x should pass through x1, y1, x2, y2. So they will be basically the same set of equations, but with slightly different numbers, letters for the parameters. So this would be d0 plus d1 x1 plus d2 x1 squared plus d3 x1 cubed equals y1, and then d0 plus d1 x2 plus d2 x2 squared plus d3 x2 squared x2 cubed, sorry. Should be white. Okay. So is that making sense so far, so good? And then, okay. So that is the most you can get just from asking the points to pass through. Sorry, just from asking the cubics to pass through the points. That's the most you can get. And yesterday, for example, when we were talking about Lagrange interpolation, and on Monday, like all the data that you wanted was the polynomial to pass through the points. The thing is that was enough because you kind of like chose the degree appropriately so that would work. Here, kind of like the trade-off is that we're not increasing the degree of the polynomials that much because we're always choosing cubics. So see, we need extra equations. That's kind of the point, right? Because kind of like the rule of thumb is that you have 8 variables. You're trying to determine 8 coefficients, like the C's and the D's, but you only have 4 equations. So in principle, there are kind of like 4 more equations you should come up with to kind of try to find like a unique solution. That's kind of like the philosophy behind the method. Okay, so we roughly kind of like, in a sense, like we need 4 more equations. Okay. Sure. Okay. So there's an extra equation that you get from asking the first derivatives to coincide, right? So notice that there's like a break of the function, like the function changes its formula right here. So an extra equation will come from asking the first derivative to coincide here, and an extra equation will come from asking the second derivative to coincide here. So let's find out what the first derivative is. Well, it would just be what? It would be, if you kind of compute it, is C1 plus 2 C2x plus 3 C3x squared. And the other derivative is kind of like the same, but with these. Actually, let me write down the second derivatives as well. Just just to have them all ready to go. So the second derivative will be, in this case, what it would be 2c2 plus 6c3, right? And the second derivative here would be, oh, I forgot the x, right? Yes, thank you, thank you, thank you. Yes, thanks, thanks. Perfect. Okay, so what I'm saying is that so they look fine right now. That they do seem okay. So what I'm saying is that we get two more equations. We get two more equations by forcing the first derivatives to agree and by forcing the second derivatives to agree. Okay, so there are two extra equations coming from that. Okay, so there are two extra equations by forcing uh, the first derivative of the first spline at the point x1 should be the same as the value of the first derivative of the second spline at the same point, and the second derivatives also coincide at that point because again x1 because we only have 3 points, so x1 is where the breakdown happens, like the breaking, like the change in the formula. Okay, and so what do they give you? You know, if you just substitute here, you would get c1 plus 2c2 x1 plus 3c3 x1 squared. That would be d1 plus 2d2 x1 plus 3d3 x1 squared. So that is like the equation that you get from the first derivative and the equation that you get from the second derivatives. So that's like the first equation. And the second equation is the 2c2 plus 6c3 x1 equals um, equals this. So that forces the first and second derivatives to agree where the definition changes. So far, so good. Is that making sense? So we had four before. We had four equations here, right? We had one, two, three, four equations, then five, six. So far we have six equations, right? We have eight parameters. Okay. So kind of we still need two more equations. That's what I want you to notice, right? So we still need, if there's even like a chance of finding like a unique solution, right? Because right now there are more variables than than equations, right? So there's no way like for it there to be like a unique solution if there are more variables than equations, and like that cannot happen. Um, so at this point there's where there's a little bit of variation on what you do. I'm just like, again, like the book discusses a couple of different alternatives. I'll just do like the simplest one, which is called to use natural splines. So to find the remaining two equations we will use natural splines, which means, what does like a natural spline mean? Like being a natural spline just means that you will ask for the second derivatives to vanish kind of like at the first and last points of the of like the at the outer at the edges of like all the intervals. So kind of like you ask like the second derivative to be zero at this point, and you ask the second derivative to be zero at this point. And that's kind of like the natural spline condition. And that has like some engineering interpretation for why that's like a useful condition. But um I mean, there is a reason why that's asked, but there are other variations. So I think the book discusses others that are called clamped splines and other things. So, so I don't want you to think that that's the only thing you could do, but like that is like the one we will use for our context. And so a natural spline would just be to ask for the second derivatives to be zero and at the first and last points. So this will ask. Which in this case, that means in our case, this means that what was the first point? The first point was x0. So in this case, it would be asking that the second derivative at x0 would be zero. And it will also be asking for what was the other color I was using? For the second derivative at x2 to be zero. So you don't want any extra conditions on the intermediate points. The thing is like the thing is like the condition, like you already again, like you want to have like the nice property of the second derivatives and the first derivatives to agree and the intermediate point. So for example, um like here, right? So the only place where there's still like kind of like some freedom left is like at the first point and the last point. um so that's why you kind of like want to add extra conditions there. um And it's just like, again, it's not the only reason. Like the why is kind of like, there are other things you could ask, but the idea is like, you don't want to ask more stuff in between the intervals, because that like has already been all exhausted. So the only place where you could impose more conditions is like at the first point and the last point. And so like in the natural for natural splines, what you well, because if there's because you want like a unique solution, so you do need two extra equations. Like in this case, in fact, like if you do the count, like even when you had more points, like you are always left with two missing equations. So if there's always two equations missing, like no matter the number of points, if you kind of keep track of all the equations, so even if there had been more points, you know, like kind of here where there's five, even with 5 points, if you ask the first derivatives to agree and the second derivatives to agree and the splines to go through all the points, there's always two equations missing. Like there's always two fewer equations if you're trying to find a unique solution. So you have to find two more equations. Like the only thing that I'm saying is that you cannot put like extra conditions here, because that could make the system inconsistent, because you already asked everything that you could ask for here about the first and second derivatives. The only place where you haven't asked about the like like the first or second derivative, like information about them is like in here. But kind of like if you were to ask something about the first derivatives, that could also mess up the second derivative because kind of so like the idea is to like ask just for the second derivatives to vanish here to have like two more equations. But again, there are other things that you can actually ask. Like there are other there are other conditions. Like this is not the only thing that you could ask for. I'm just saying that you had to ask for two more things so that you have like enough equations, so that you have a unique solution. Because otherwise, there's no unique solution, and then there's no like algorithm. If you think of an algorithm as being something that gives you like a unique solution, you see. But yeah, there are other types of splines. Like this is just like one type of possibility. Like what I'm trying to kind of like say is that like the two equations that are missing cannot be found in between because in between you already asked everything about the first and second derivatives. It's only at the endpoints, at the like endpoints in the literal sense, like at the really first point and the last point of this like big interval where you still haven't like asked like all the equations. You see. But yeah, there are other things like you could ask for, which the book discusses. But like kind of like the natural condition, like the natural splines are kind of like the easiest ones to state because it's just like equating the second derivatives to zero. So that gives you like the two extra equations that are after. So in this case, let me see. Right. Oh, sorry, this should have been next to. Okay, let's I'm about to show you, like, I think it's good to do this like with a particular example. So I'll do it for the 3 points that I had shown you earlier on GeoGebra. Solve like the system of equations. It's going to be linear equations, so it won't be that bad. But let's do a 5 minute break quickly, just in case like someone wants to ask me something. If not, I'll just quick do the spline for a particular case, and then we can do the quiz. But it's maybe good to have like a small breakdown here before we do throwing ourselves into the example. So let's say 11:30. Okay, so yeah, let's do a concrete example. I mean, as you can see, there are 80 equations to solve. So like in order to have simplifications, like some of the points, like the points basically need to have like nice coordinates. So like I'll do, so that it's not like too tedious to solve by hand. So, I'll do kind of like one like the one that I showed you earlier on the algebra, but one of the coordinates is zero because that makes your life very easy. So otherwise, it would just be it's like just like a problem of linear algebra. Like it's kind of like so. So let me do an example where we want to find the spline, the natural cubic spline, passing through. So the points that I gave on GeoGebra were -1, 1. Oh, 0, 0. That's going to be nice. 0, 0, and 1, -2. So this is x0, y0. This is x1, y1, and this is x2, y2. Okay. So basically what I'll do is just take the equations that we just found and like plug in these values. And again, just like because the numbers are nice, like you'll see it does simplify like significantly. So let's just go. Sorry, I'll do some copy pasting because otherwise it's like a bit um so like the first two equations were these. These were like the equations for the first line, right? So these ones become, what do these ones become? They become here like x0 is -1, right? So x0 is -1. So it becomes c0 minus c1. -1 squared is 1. And -1 cubed is -1. Okay, so that gives you c0 minus c1 plus c2 minus c3 equals 1. Okay. And then the other one becomes, oh, this is great. The other one, because x1 is 0, right? Whoops, goes. Okay. So it just gives you that C0 equals Y1 and Y1 is also 0. Okay, so that one wasn't that bad, right? Like, well, I mean, of course, I'll write down all the equations first, but let me put them in a box. Okay, so that's what you get from the first spline having to pass through -1, 1, and 0, 0. Okay, then let's go with the others. Let me copy paste. So these ones become what what happens here. So again, x1 is 0. So this one just becomes the d0 equals 0. Okay, and for the other one, x2 is 1 and is with -2. So it becomes d0 plus d1 plus d2 plus d3 equals -2. Is that okay? So far, so good, making sense? No, there's well, if you look at the study guide, if you look at the study guide, which I'll mention maybe tomorrow, there's like actually like a fast. I guess I'll mention it tomorrow. There's like a faster way to find the equations. Um, but um, but right, you do need to set it up. Like what you need to remember is the just like the matching conditions, like that they should match, that it has to go through the endpoints, and that the derivatives coincide, and that the second derivatives coincide, and all this stuff. But there is like a slightly different way to set it up, um, using like the Lagrange interpolation, where I mean you would never memorize these equations in any ways in practice. You would just write like the formula of the two polynomials, right? And like, there's no point in memorizing them. It's better to derive them. But I'm just saying, like, there's like a slightly faster derivation, which I'll mention like next time, um, tomorrow, with the Lagrange interpolation formula. But yeah, like no one would ever like I would never expect anyone to memorize these because like yeah, it's just easier to write like the cubic polynomials and take all the derivatives. Um, but yeah, there's like a slightly better method to do it. But I wanted you to kind of like see it like from scratch, so you have like like an idea of like how like the thing, like the advantage of this doing it this way is that you kind of like see the count of equations, that you're it makes it more clear that you were missing two equations, that there were two extra equations needed. The way I'll do it tomorrow, that's not super clear. So it's kind of like more transparent to see why you needed more conditions in this from this perspective. But the one that from tomorrow will actually be a lot easier to kind of like work with. Um, and I'll solve this again tomorrow with the other perspective. And that is almost nothing to memorize. Like, it's like very straightforward. Um, but this one is kind of like better to kind of look at the count of parameters. Okay, like how many equations do we need left and things like that. Um, and like if you look at the study guide, like the study guide, I explained it um, in with the other point of view, but I'll kind of like go over that tomorrow. And then, okay, where am I? Am I getting? Okay, so then this is the then we had these two extra equations which were like coming from the first derivatives. These ones are also easy, right? Because x1 is 1, 0. Become so it just becomes that c1 equals d1, right? And kind of like the d2 c2 equals d2 as well. Okay, and the last equations needed. So it's once you have like specific values, especially one of the values is x, that is equals 0, which I'll probably just give you one like that. So like it's not too bad. Like once you have that, like the system of equations that you have to solve is not too bad. But yeah, like tomorrow I'll do it in a slightly different way where um simplifies a bit better. And then the last equations, then these ones become okay, so what happens here? X0 was -1, so it becomes 2, C2 minus 6, C3 equals 0. And this one becomes, and then X2 was 1, right? So this becomes 2D2 plus 6D3 equals 0. Okay, so now, like those are the ones that you would have to solve, but they it's I'll put everything together, but you'll see that we already have plenty of information. So the system of equations that you have to solve is not as bad. So we need to solve. Well, I'll put it like I'll just leave one of these ones. I'll use the fact that C0 equals 0. I'll keep that as already as a fact to use. So this is an important fact. So this equation doesn't matter anymore. Then the other fact that was important was that D0 equals 0. So like only the last equation matters here. So again, D0 was 0. So this one is like this, right? Then what was also okay, these are already, I mean, they are these two also they're like already simple enough. That will allow you to replace D1 and D2 in terms of C1, C2. So I'll use it that way. So D1 is C1. Okay. And then and the okay, so and then the last two are these ones. Okay, but again, in this system of equations, I can use the fact that um, D1 is C1 and D2 is C2. So where is D1? D1 is here. So I'll replace D1 here with C1, and I'll replace D2 here with C2 also. And then I'll replace D2 here with C2. Okay. Is that okay? Is that making sense? And so how many, let's see if everything is still fine. So what are the unknowns here? So what is still unknown is C1, C2, C3, right? And D3, right? There are four things that you still don't know, and you have four equations. So this is perfect, right? And then if you do like for example, what can you do here? Like for example, like the easiest ones to work with are the last two because they're set equal to zero. So here you could like for example subtract 3 minus 4. So if you do 3 minus 4. Well, I guess now, like, lucky that I'm solving it. Even here, like, it's kind of long, so I may just ask you to set it up. But I'll think like I do want to solve it everything so that you see like the spline because yeah, like solving the system of equations, like, does take a little bit more time, even when the numbers are nice. So if you do 3 minus 4, you get 2C2 minus 6C3 minus 2C2 plus 63 equals 0. Um, so the C2's cancel. That's why I kind of wanted to subtract them. So you get that minus 6 D3 equal minus 6 D3 equals 0. So what does that tell you? That tells you that D3 equals negative C3. Okay. Okay, so that's another important piece of information. Um, the D3 is minus 6 C3. Okay, so that way you can keep up. That way you can keep the first three equations using that information. So, so if you keep the first three equations, but you use the D3 is minus C3, so now that's how the system looks like. So again, three unknowns, three equations. Right, like three equations, three unknowns, perfect. So we're still good, keep good track. And then like the others are not too bad. Like like we're almost at the end. Uh, this is not too bad to solve either. Like it's just what would be the easiest thing that you could do? Like yeah, you could for example, you can solve for C2. That's what I would do first. Like you can say that C2 is 3C3 from 3. And so you substitute that into the remaining two equations. So you substitute. Okay. Whew, we're almost there. So what does that give you? The system of equations simplifies to minus C1 plus 2C3 equals 1, and C1 plus 2C3 equals -2. And if I make any mistakes, like just let me know. Otherwise, everything will get messed up. Um, okay, and this is very easy to solve if you add the equations together, right? So if you add if you add the equations, these two cancel. So you get 4C3 equals -1, and so C3 equals -1/4. And that kind of like is domino effect, because once you have that, then you do know all the others, right? Because what is C1 then? C1 would be -2 minus 2C3. -3/2. And that is enough to like pin down everything, right? Because so summarizing, so what was C0? C0 was 0, if not mistaken. C1 is -3/2, right? What is C2? C2 is 3C3. Okay, so that's 3C3, so that would be -3/4. And C3 is -1/4. And that gives you the course. And from there, you also have like the D values. So D0 was 0. What was D1? Sorry, just to go back for a second. According to this, D1 was the same as C1. Perfect. And then what is D2? According to this, D2 was the same as C2. And what was D3? D3 was minus C3. So D3 would be 1/4. So that means that the first line, would be -3/2 x minus 3/4 x squared minus 1/4 x cubed. And then the second spline would be, it's very almost the same, right? Of course, like it's almost the same because I chose like very nice, convenient numbers. Otherwise, you would expect them to potentially be quite different. So it is because like of like the very convenient choice of numbers that they kind of like end up just looking like this. Let me see if I can show you that on GeoGebra. Second. That would also verify if I made any mistakes, like which would be very frustrating. But yeah, I think this probably takes too much time to ask. But I would ask you at least to set up the system of equations that you have to solve. And tomorrow I'll tell you a different way to set it up, um, which is a little bit more efficient. So like, but yeah, if you just set it up, then that's fine. Like that doesn't take too much time. Um, so you can set it up either using this method with all these coefficients, or like doing it like the way I'll explain tomorrow. So, but yeah, solving the system like just like takes forever, and even this one was like a bit simple. So the first cubic, let's call it S1 of x. Let's see. The first line would be minus 3/2 1.5 x. Okay, at least it looks good in like in the sense that it does pass through the 2 points, so that's good. And let's see. Okay, so is this red curve that you see here? That's the cubic, right, corresponding to this formula. And then the second spline would be between 0 and 1. It's almost the same as I was saying, but it's with the plus, right? Oh, and it should have been, let's see, would it have been? It should have been 25, not 20.20. It should have been 0.25, not 0.24. So let me fix that as well here. Whew. And there it is. So that's the second spline. So kind of like hopefully you can tell it does look smooth, like in the sense like the first derivatives match. So like there is like a tangent line to the curve at this point where like and they also like the concavity is kind of like fit together nicely. So in both cases, like the second derivatives don't like abruptly change, don't change abruptly at the breaking point, which is also what you want to make sure of. Uh, in fact, like it's concave down, kind of like on this on the well, I mean the concavity, yeah, it's concave down here, so there's no abrupt change in the concavity. Like, let me see if I can show you this. Um, yeah, okay, yeah. And again, I will put for some who are interested in reading more about this, I'll put like something about how like splines are used in regression models, like that, just to for you to have like a bit more like information about how this is all. This is like in matrix format, so you can tell that it is kind of like long and annoying. But I'll let that for those who are interested to know about how splines are used for regression, that you can read about it. And then yeah, and this also kind of like talks a little bit about the drawing his example that I mentioned yesterday, how splines compare to like in Lagrangian interpol well, like in this case like linear regression, but there's like another source that I'll post. Like again, if someone is interested in learning more about this, like about which compares like the Lagrange interpolation with this approach using splines. So um let's see. Oh, like yeah. So here's kind of for examples for this wrong hit function or like a variation of that. It would look with splines versus how it would look with like Lagrange interpolation, and you see kind of like it wiggles more if you use Lagrange interpolation. Um, so like again, for those who want to learn more about this, because kind of like the reason why I chose to talk about splines is because like splines is very used. So in practical stuff. So like it's just that we cannot go into much detail and all those uses, but like this at least should give you like an idea of how you set it up, you know, like kind of like why you needed this extra two conditions and the derivatives, etc. Okay, but I think this is a good place to stop here. I'll just make the quiz available. so that you can go take it, unless you want to ask me something, in which case I'll also happy to stay here to chat. If not, I'll see you tomorrow. Yeah, you can use calculators for either quizzes or exams or whatever. Yeah, but um, but yeah, what I was saying is like something like solving the system of equations like this for the spline. It just takes forever. Like I would just ask you to set it up, because otherwise, it's just like a linear algebra problem. You would put it on Wolfram Alpha or like MATLAB to solve the system of equations. You know what I mean? But at least it's kind of useful to see. It is useful to work out on your own when you have time, some examples, so that you see how much effort it takes. Like that makes you appreciate like kind of like being able to put it on a computer if you kind of like do it from that perspective. But yeah, you can use calculators. I'll update the study guide just to say that I would just ask you to set up the system of equations you would need to solve. You too. Anyone else? Bye bye. See you.